Hi, my name is Albert, and as I want to keep this video short, I have abridged this presentation to around 9 minutes rather than the usual 15. So only the core information has been shown here for your viewing. Now, I want to start this off by saying that we want to ensure safety for humans in the long-term presence in Leo and beyond. But one of the issues that we need to address for that to happen is to fill this gap in knowledge in the understanding of long-term effects of partial gravity on the human body and mind. Now, so the proposal is a variable gravity research platform which orbits the Earth in Leo. Now, I understand that we cannot just go about doing that in just one big step. So I've adopted a phased approach where phases 1 and 2 shown here are the test beds leading up to the research platform. And so my thesis becomes a test bed rather than the research platform itself. Now I want to achieve a low-cost enabling mission by using off-the-shelf products which will reduce developmental time and costs, which will help us to understand human adaptations to rotating environments. Alright, so let's see what the design concept looks like. It's basically a three-body system, two space vehicles tethered to a pressurized central hub, and this central hub docks to the International Space Station in its rest condition. For the space vehicle, I've chosen the Crew Dragon according to these evaluation criteria listed here. And similarly for the central hub, I've identified the module plus the Progress as candidate, but this might change as the thesis goes on. And so this testbed starts looking something like this, but with two Crew Dragons instead of one. And now once I had my concept in place, I could begin identifying my test objectives. First, the technical ones. We can test subsystems like ECLIS, thermal controls, GNCs, and so on. We can test docking and transfer systems and protocols. We can test the spin-up and spin-down systems and protocols. And also we can test the structural stability and the integrity of the system. And now for the physiological test objectives, we can test the human body's response to Coriolis forces and other related effects. We can also test the human body's response to the different levels of G and the varying levels of RPM and the radii used to achieve these gravitational conditions. Now, once I had my test objectives in place, I started exploring how this testbed might be launched and operated. So first we will launch the UA module plus the Progress as the central hub. Now the central hub docks to this Zvezda module. Then we launch a modified Crew Dragon and we dock it to the central hub. Now we can launch the second Crew Dragon and dock it to the other side of the central hub. Also, we might need to perform an EVA to hook up the tether system and check for anomalies. Right? And then we can enable the docks mode on to get the testbed ready for operation. Now, after all that, we can actually start performing the technical test operations, right? So we can switch it to the free flying mode where the central hub solar arrays are folded and all the systems are turned on. So we undock, and after it reaches a safe distance, it does a flip to orient the Progress thrusters towards the ISS. Now we can fire the Progress thrusters as we accelerate towards the test operation zone. Now we park at the test operation zone, which is defined to be at the edge of the approach ellipsoid on the aft side of the ISS, which gives us about a 2,000 meters separation. Now once there, we can fire the thrusters that are augmented onto the service module of the Crew Dragon to start the spin-up. Now as the Dragons are undocked and released, a spring is loaded which is on the tether system, and we can lock the spring using a clutch mechanism when the desired radius is reached. Now we can go ahead and perform experiments for T1, and after that, to spin down, we can fire the retrograde thrusters on the dragons. The springs, which was earlier loaded upon the release of the tethers, it can now aid in collection of the tethers. Now we can also fire RCS intermittently to maintain tension on the springs, on the tethers rather. And so as the dragons dock back to the central hub, we can fire the thrusters on the central hub to return to the ISS and dock back. Now we switch back to the dock mode to recharge the batteries and prepare the testbed for the upcoming series of tests. And after that, we can start performing the designated tests, both technical and physiological. From the ConOps, I identified some functional requirements of the project. First is that the testbed should be able to act as a free flyer with its own subsystems for short durations of the test operations. An in-orbit refueling ability to keep the operational lifespan of the testbed relevant will be needed. Also, we can remove the internal outfittings of the Crew Dragon so that we can make space for experiments to be performed. And because we're not going to launch humans, we can remove the Super Draco thrusters. Instead of that, we can introduce thrusters in the service module of the space vehicle, and also hooks for the tethers to be attached. Now I did some mass and cost calculations. Here's a ballpark figure where the quantities shown with an asterisk are my estimates. So the total cost of the project could be around $24 million, and the total mass could be around 31 metric tons. Now, as for the augmented thruster calculations, I have assumed some conditions here. Please feel free to pause the video and check them out. If we assume that we use something like the KDTU-80 thrusters used for the Progress, we can have to expect around 11 spin up and spin down cycles before we need to refuel. Now it's important to note that I am at the beginning stages of my quantification, so I will make it more detailed as I go along. Now, the scope of the project includes things like the mission architecture, the basic understanding of time taken, forces needed, and so the technical systems needed to achieve those forces. Also basic modifications needed to the Crew Dragons and Central Hub, and the basic design of the tether system. And things which lie outside my scope are things like the design of the subsystems themselves, the physiological test activities to be performed, and the interior design of the testbed. Now in the coming few months, I'm going to design the tether system. I'm going to detail out the augmentations needed for the space vehicle as well as the central hub, and I'm going to do more quantifications to check the feasibility of this proposal. And so in conclusion, I'd like to point out that I'm taking a stab at how to break down artificial gravity application into digestible pieces. And an understanding of the long-term effects of partial gravity on human physiology will be essential if we need or if we want to send humans to places like Mars one day. And so I like to ask myself this question, and it's that what bridges need to be built from the current state that we have right now to the future state that we want to achieve. And this thesis proposal is one of those bridges, is my argument. Thank you.